morning. In today's lecture, we're going to be discuss about the completeness property in a nonlinear space. So now, first of all, we discuss about the convergence. Let a sequence xn in a nonlinear space X. A sequence is said to converge to X if for a given epsilon greater than 0, there exists a natural number n such that norm of xn minus x is less than epsilon for all n greater than or equal to n. Equivalently, sequence xn converges to x if norm of xn minus x limit converges to 0. If this is the case, we shall write xn converges to be x or limit xn is equal to be x. Convergence in the norm is called a norm convergence or strong convergence. The sequence xn is called a Cauchy sequence if for a given epsilon greater than 0, there exists a natural number n such that norm of xn minus xn is less than epsilon. So let X be a nonlinear space and A be a non-empty subset of Ax. Then few properties over a norm that modulus of a dxa minus dya is less than or equal to be norm of x minus y for all xy belongs to be x, and modulus of a norm of x minus norm of y is less than or equal to be norm of x minus y for every x and y belongs to be x. If xn converges to be x, then norm of xn converges to be norm of x. If xn converges to be x, yn converges to be y, then xn plus yn converges to be x plus y. If xn converges to be x, alpha n converges to be alpha, then alpha n xn converges to alpha x. Every Cauchy sequence is bounded in the nonlinear space. Every convergent sequence is a Cauchy sequence. So now I'm going to prove it out, these properties. So for any A belongs to be capital A, the distance between an element and a set is less than or equal to be norm of x minus A, which is further less than or equal to be x minus y plus norm of y minus A by using a triangle inequality property. So d of x comma A is less than or equal to be norm of x minus y plus d of y, or d of x comma A minus d of y comma A is less than or equal to be norm of x minus y. And interchanging the role of x and y, we get the given result out to be proved out. And similarly, two will follow from the first by taking the set to be a null set, zero set, having element 0. And third number follows from a set 2. And similarly, using a triangle inequality, it is easy to prove the question number 4 and the question number 5. Now we prove the 6. So let xn be a Cauchy sequence in X. Choose n1 so that norm of xn minus the xn1 is less than 1 by considering the epsilon as a 1 for all n greater than or equal to be n1. So by the property number 2, norm of xn is less than or equal to be 1 plus norm of xn1 for all n greater than or equal to be n1. Thus, the norm of xn is less than or equal to the maximum of norm of x1 plus on norm of xn minus 1, comma 1 plus norm of xn1 for all n. And this was possible only if we have a norm of xn is less than or equal to be something. So you can say that the Cauchy sequence is a bounded sequence here. And now we are going to prove it out, the property number 7. The property number 7 is going to say that every convergent sequence is a Cauchy sequence. Here let that xn be a Cauchy sequence in X and converges to be X. Suppose that for a given epsilon greater than 0, there is a natural number n such that norm of xn minus x is less than epsilon by 2 for all n greater than or equal to be n. And for n comma m greater than or equal to be n, we have norm of xn minus xm is less than or equal to be norm of xn minus x plus norm of x minus xm, which is less than x epsilon by 2 plus epsilon by 2. is equal to be epsilon, the sequence xn is a Cauchy sequence. And let X be a nonlinear space over a field F. A Cauchy sequence in X which has a convergence subsequence is convergent. So let Xn be Cauchy sequence in X and Xnk be its subsequence which converges to X belongs to be capital X. Suppose that for a given epsilon greater than 0, there is a natural numbers n1 and 2 such that the norm of xn minus xm less than epsilon by 2 for all n and m greater than equal to be n1, and norm of a subsequence xnk minus xk is less than epsilon by 2 for all k greater than equal to be n2. And take the n as a maximum of these two elements n1 and n2. If k is greater than equal to be n, then since nk is greater than equal to be k, we have norm of xk minus x by using a triangle inequality is less than epsilon by 2 plus epsilon by 2, which is equal to be epsilon. Hence, xn converges to be x. A metric space xd is said to be complete if every Cauchy sequence in x converges in x. And a norm-linear space that is complete with respect to the metric induced by the norm is called a Banach space. So let X be a Banach space and M be a linear subspace of X, then M is complete if and only if M is closed in X. Assume that M is complete. We have to show that M is closed. To that end, let X belongs to be closure of M. Then there is a sequence Xn in M such that the norm of Xn minus X converges to be 0. Now since sequence Xn converges, it is a Cauchy, and completeness of M guarantees the existence of an element y in M such that norm of xn minus y converges to be 0. And by the uniqueness of a limit x is equal to be y, hence we can say that M is closed. For second converse part, assume that the M is a closed, and now we have to show that the M is complete. So let xn be a Cauchy sequence in M, then sequence xn is a Cauchy sequence in X, and since X is complete, there is an element x in X such that the norm of xn minus X converges to be 0, but then X belongs to be M, and since M is closed, hence M is complete. So now we are discussing some of the examples so which we can check it out whether we can talk about the completeness. So now first is we have to show that if X is a Rn or Cn unitary space is complete if we choose a metric dxy is equal to the summation of xi I minus eta I square whole is to power 1 by 2, where x is xi I and y is eta I, which belongs to be x. So first of all, we'll prove it out the first property, the first proposition, A part. And we have similarly, we have so many examples out here. Let x is equal to b, L infinity is complete if we choose a metric dxy is equal to supremum of a xi I minus eta I whole square. And further we have x is equal to be LP. We have already discussed about the LP space out there, and we will define the metric dxy is equal to summation of a xi I minus eta I power p whole is power 1 by p. Anyhow, so first of all we'll discuss case number 1, when the dxy is being defined as the xi I minus eta I square whole to the power 1 by 2 over the Rn. So now say we have condition number A. So dxy is being defined like this way. Suppose that the xn is a Cauchy sequence in X, where X is equal to be a finite dimensional space, where xm is equal to be xi1m, xi2m, and so on xi so for a given epsilon greater than 0, there exists an integer n such that for m and n greater than equal to be n, we have a dxm comma xn is equal to be this one by using a definition of a dxy is less than epsilon. Squaring on both sides, we get summation of xi I minus eta I square is less than epsilon square. So we get this part is less than epsilon, and this shows that for each fixed I, The sequence xi I1, xi I2, and so on is a Cauchy sequence for real numbers, and we know that R is a complete. Every Cauchy sequence in R converges. Say that this xi I m converges to be xi I as m converges to be infinity. Now, as x is equal to be xi1, xi2, so on, xi n. So take up the n converges to be infinity in this equation. And of this equation, when the n converges to be infinity, this xn converges to be a xi x out there, which is equal to be xi1, xi2, so on, xi n. So this is equal to we get dxm comma x is less than epsilon. Hence, we get the part that the xm converges to be x, which belongs to be Rn. So we can say that it is a complete. Now, similarly, now we're going to be show up that the second case in which we have considered the question like x is the L infinity and the dxy is being defined as supremum of a xi I minus the eta I square. Now we have to be show that this is the required complete. So now we're going to prove out the second part. Say that xm be a Cauchy sequence in L infinity. So xm is being defined like this way. And since the metric defined on L infinity is being given by dxy is the supremum over the I xi I minus the eta I, and x is equal to be xi I and y is equal to be eta I. So for a given epsilon greater than 0, suppose that the given the sequence here we are considering as a Cauchy sequence. So we have a dxm comma xn is equal to be supremum is less than epsilon. And for a fixed j, on the same lines of the above example, we have a fixed j, we have a the modulus of a xi jm minus a eta jm is less than epsilon. And for every fixed j, the sequence is a Cauchy sequence in R, and since the R is complete, so it converges. So xi jm converges to be xi j, and here we have this is less than epsilon. Since xm belongs to be L infinity, so there is a real number km such that xi jm is less than equal to be km. Hence, by triangle inequality, we have a modulus of a xi j is less than equal to be xi j plus minus of a xi jm plus xi jm is less than equal to be epsilon plus km. And this inequality holds for every j. And the right hand side does not involve a j. And xi j is a bounded sequence of numbers. And this implies that x belongs to be L infinity. So we obtain that xm converges to be x, and hence, and where the x belongs to be L infinity, and hence L infinity is a complete. On the same lines, you can prove it out that the LP space defined over the this metric is